In Chapter 2, we looked at the time-dependent diffusion equation, or heat equation. Heat conduction is basically just diffusion of heat. And here's the one-dimensional version. The two-dimensional version, of course, has a UXX term. Now, if you let the time-dependent diffusion equation run until it reaches a steady state, then obviously U sub t will be 0 then, because U is not changing with time, and you have a 0 here, and this is called the steady state equation. That's what we're going to study in Chapter 4. And here is our steady state one-dimensional diffusion equation with boundary conditions. It's actually an ordinary differential equation with boundary conditions, but we'll also be looking at the 2- and 3-dimensional versions of this. Now in Chapter 4, we're dealing with steady state boundary value problems, not time-dependent initial value problems, and stability is no longer a big issue. It was a big issue in Chapters 2 and 3 because many reasonable-looking finite difference approximations for the time-dependent problems turned out to be completely unstable. That just isn't an issue for steady state problem. However, the steady state problem sometimes doesn't have a unique solution, whereas the time-dependent problem always does for reasonable coefficients. In fact, here's a simple steady state boundary value problem that doesn't have a unique solution. This problem, in fact, has many solutions. If I change one of the end conditions, let's say U of 1 equals to 1 instead of 0, then it actually has no solution. So a steady state problem, there's no guarantee of a unique solution. No guarantee in general, that is. On the other hand, if we assume A of x is less than or equal to 0, and of course we're assuming the diffusion coefficient is strictly positive. If we assume A of x is less than or equal to 0, then there is a guaranteed unique solution to this problem. And in fact, the usual finite difference approximation to it is guaranteed to be weakly diagonal dominant. And if A is strictly less than 0, it's guaranteed to be strongly diagonal dominant. In either case, that means we can do Gaussian elimination without pivoting. And for the 1D problem, we have actually a tridiagonal system because the ith equation involves only 3 unknowns, so you have to solve a tridiagonal system to solve the steady state problem, 1D problem. Now in the next section, we look at a nonlinear steady state problem, again one-dimensional just to keep it simple. This is nonlinear because the ux square and the u square terms, if we use the usual finite difference approximations to uxx and ux, that is centered second order approximations, we end up with a nonlinear system because the squares here. So we have our discrete finite difference system is nonlinear. We take everything on one side, leave 0 on the right hand side, and the left hand side we're going to call that f sub I. So we're trying to solve a system of nonlinear equations, f sub I equal to 0 for I equals to 1 through n minus 1. Now how do we solve nonlinear systems? Well, nearly always we use Newton's method to solve them. Newton's method is an iterative method. Every iteration we have to solve a linear system where our right-hand side vector is our vector of f's, the f sub i's we were just talking about, and the matrix is the Jacobian matrix, which is a generalized derivative. Jacobian matrix, its ijth component is the partial of fi with respect to uj. And then after you solve that linear system for the vector delta, you simply subtract that delta from the old u vector, and that's your new approximation. Typically Newton's method, if it converges, will converge in a small number of iterations, 5 to 10 usually. If it hasn't converged by 10 iterations, often it isn't going to converge. It also, whether it converges or not, can be highly dependent on the initial values given for u. Okay, so for this problem, our F vector, here are the components of f sub I, the components of f, and the Jacobian matrix is tridiagonal because the ith elf depends only on ui plus 1, ui, and ui minus 1. All other partial derivatives of fi with respect to uj are 0. So the Jacobian matrix is tridiagonal, and here are the three diagonals. That's just the partial of fi with respect to ui, minus 2 over delta x squared, so forth. This is the partial of fi with respect to ui minus 1, and so forth. So every step of Newton's iteration, we have to solve a tridiagonal linear system, and then the solution of that we subtract from u. Here's the Fortran program. As usual, there's a MATLAB program in the appendices. It's actually extremely simple program. U of 0 is set to the left-hand boundary condition. U of n is set to the right boundary condition. U of 1 through n minus 1 we initially set to straight line connecting the two boundary conditions. Could just set them equal to 0, but it may be important to have better starting values. And then we do a maximum of 15 Newton iterations. Each iteration we simply calculate the vector f, that's just the left-hand side of our finite difference equation, and where the right-hand side is 0. And then here are the three diagonals of the Jacobian. That's partial of fi with respect to ui minus 1, with respect to ui plus 1. And then we call this tridiagonal linear system solver that we wrote in chapter 0, with elf being the right-hand side. There's the three diagonals of the tridiagonal system. There's the solution, comes back delta, and you simply subtract the delta vector from the u vector, and that's 1 Newton iteration, and then we stop when it's converged. Here are the results. It looks like whenever you double n, that is cut delta x in half, the error goes down by a factor of about 4, which is what you would expect for a second order method. The truncation error is second order because the approximations to uxx and ux that we used are centered second order approximations. In the next section we solve a linear 1D differential equation. We end up with a tridiagonal system as expected, and we solve that. And the interesting thing about this problem are the results. Here, when we cut h by a factor of 2, the error only goes down by a factor of a little more than 2, and we're using second order finite difference approximations to uxx. So we expected order delta x squared, and we're only getting order delta x about 1.1. What's the problem here? Well, the problem is that the exact solution is x to the 1.1 power. If we look at the truncation error, let's go back to chapter 1, where we saw the error between the usual centered finite difference approximation to the second derivative is h squared times the fourth derivative of u over 12. And we've said that stability is not a problem in chapter 4. In other words, the methods are always stable, basically. That means the truncation error and the error are proportional. And the problem is, even though it looks like it's second order, there's h squared, the problem is this fourth derivative of u, in the case that u is simply x to the 1.1 power. If you take 4 derivatives of that, you get x to the minus 2.9 power. And since our interval was 0 to 1, near 0, the fourth derivative blows up. So basically this is h squared times infinity when t is close to 0, x is close to 0. So the problem here is the truncation error is not really delta x squared, it's delta x squared times fourth derivative of u, but the fourth derivative of u is unbounded because u is x to the 1.1 power, which has a bounded first derivative but unbounded second derivative in the interval 0 to 1, and fourth derivative is unbounded. So actually what we need to do in this case is use a non-uniform step size, make the delta x smaller, closer to 0 where the problem is. That's a little difficult to do with finite differences. We're going to do that with finite elements later on in chapter 5. Okay, now let's talk about 2- and 3-dimensional problems, steady state problems. The simple steady state diffusion or heat conduction problem with a source term F in 2 dimensions might look like this. And we use the usual finite difference approximations, and we get a linear system again, but of course now it's not tridiagonal. It's, let's see what kind of form it has in the 2-dimensional case. It's a linear problem, and the finite difference approximation, you have to solve a linear system. The linear system looks like this. We've talked about this before in the implicit methods in chapters 2 and 3. You have to solve a linear system like this every step. Here we only have to solve one, but it has a banded structure, but as we mentioned before, inside the band it's mostly zeros, so a band solver is certainly better than a full linear system solver like LINEQ, but it's still not taking full advantage of zeros. It takes advantage of the zeros outside the band. It ignores them, but the zeros inside the band fill in, so even a band solver may not be the most efficient solver. We talked about sparse direct solvers in chapter 0. They're generally better than the band solvers, very complicated to write, but we can do even better than either one of those for a lot of steady state problems, at least, not for general ones, but by using iterative methods. And here's a typical linear system for a 3-dimensional problem. Again, it has a band structure, but there are a lot of zeros inside the band, which leads you to think that maybe it's possible to do better than a band solver, and in fact it's possible to do even better than a sparse direct solver, because even the sparse direct solvers have some fill-in. Iterative methods take full advantage of zeros, so when they converge they may be faster than direct solvers, so we're going to look at iterative solvers now. We're actually going to talk about nonlinear systems. Linear systems can be solved by any method that solves nonlinear systems. Just a special case of a nonlinear system that happens to be linear. Remember that we said normally you use Newton's method to solve nonlinear systems of equations. Well, in the 1D case that is good. The Jacobian matrix is just tridiagonal typically, but in 2- and 3-dimensional problems the Jacobian matrix will have the kind of structure the linear systems we just looked at, and so of course you can use Newton's method, but every step you have to solve a linear system that looks like that, and it may be inefficient. One of the most popular iterative methods for linear or nonlinear systems, we're going to develop it for nonlinear systems, is the nonlinear over-relaxation, or it's called successive over-relaxation method for the linear case. And it's really can be thought of as just a variant of Newton's method. Recall that Newton's method, every iteration you have to solve a linear system where the right-hand side is the vector in the linear system, F equals 0, and the matrix is the Jacobian. And for 2- and 3-dimensional problems, each iteration of Newton's method is like solving a linear system similar to those we've just shown. They may be very expensive. So the idea behind the nonlinear over-relaxation method is simply we throw away everything in the Jacobian matrix except the diagonal. Just change everything to 0 except the diagonal. Now that obviously is not a good idea in general for general nonlinear systems, but if the diagonal part is large compared to the rest, and we've seen that in most of our examples the diagonal part is large. We had 6s down the diagonal in 3D case and 4s down the diagonals and -1 scattered around. So you simply throw away everything in the Jacobian matrix except the diagonal part, and obviously that won't work for all systems. In fact, if any of the diagonal elements are 0, you won't even be able to take one iteration. You'll get divide by 0. But let's consider that. So we just throw away everything in the Jacobian matrix except the diagonal part. That seems pretty obvious that that's going to require a whole lot more iterations, because it may be a poor approximation to the Jacobian that we're using. However, each iteration will certainly take a whole lot less work because it's so much less work to solve a diagonal system. So that's the idea behind nonlinear over-relaxation. You have a system of linear equations here, and you basically are using Newton's method, but with the Jacobian matrix replaced by its diagonal part. Throw away everything except the diagonal. That means each iteration is a whole lot less work because you're basically just dividing by the diagonal elements. See, here's the diagonal partial of fk with respect to uk is the kth element of the diagonal Jacobian. So we're just taking the diagonal part inverse times elf and subtracting that from u. However, you'll notice there are two other small differences between this and Newton's method besides the fact that we're just throwing away everything off the diagonal. One is we've got this omega parameter here that we're going to have to talk about. If it's 1, which it is for the Gauss-Seidel method, which is a special case, then it's the same as Newton's method in that sense. The other, but we'll actually be using values of omega generally larger than 1. We'll talk about the values of omega in a minute. The other difference is, notice that with Newton's method, the elf and the Jacobian elements are all evaluated at the current unknowns. Here we're using the latest calculated values. In other words, if we're calculating u sub k, we assume we already have new values for u1 through uk minus 1. Why not use them? With Newton's method, you can't do that because you update all the unknowns simultaneously and after you solve the linear system. But here we're updating them one by one, so why not use the new values, the n plus 1 values of u1 through uk minus 1. We have to use the old values of uk through um because those are the latest values. So basically what we are evaluating both the components of elf and the components of the Jacobian matrix. We're evaluating them all at the latest values of each variable. As soon as we get a new approximation for one of the components of u, we go ahead and use it on the right hand side. Seems reasonable. So the NLOR can be thought of as simply a variation of Newton's method, where the main difference is you throw away everything except the diagonal, which makes it a lot less work per iteration, but as you may expect, it takes a lot more iterations. And then we have this funny parameter omega here, and then we're using the new values of u as soon as they're available rather than waiting until the next iteration. Of course, NLOR, designed for nonlinear systems, can be used for linear systems also. In fact, usually is, where your elf is just AU minus B. Elf can be a linear system. And it's not at all obvious that this is going to converge. Throwing away everything except the diagonal part of the Jacobian sounds like it might be a bad idea. But we do have some convergence theorems. The most important one, perhaps, is the following. It says that if your A matrix, remember we're applying this now to a linear system where elf is, the vector elf is simply AU minus elf, it's a linear system. If A is positive definite, then this method, which is called SOR in the linear case, is guaranteed to converge for any value of omega between 0 and 2. In fact, in practice, we're going to always have omega between 1 and 2. It's not obvious why, but at least the theorem guarantees that in the positive definite case, it's guaranteed to converge for omega between 0 and 2. Then there's another theorem in the same section that says if A is diagonal dominant, the SOR method is guaranteed to converge if omega is between 0 and 1. We usually are going to use it for omega greater than 1 despite this theorem, but at least it's guaranteed to converge for omega equal to 1. And the omega equal to 1 case is called Gauss-Seidel iteration, and it's important in its own right. So we see that both positive definiteness and diagonal dominance are good qualities to have, not only if you're solving a linear system using a direct method, then you don't have to worry about pivoting, but SOR at least is guaranteed to converge for both cases, at least for some values of omega. Okay, let's try it out on a two-dimensional problem. Here's a linear system, boundary conditions on the square. We use your usual finite difference approximations to the second derivatives, and we get a big linear system. Notice there's a parameter a in the differential equation, partial differential equation. We didn't specify a value for it. We're going to play around with that parameter. It's shown in the section 4.7 that as long as a is larger than minus 2 pi squared, which is about minus 20, so if a is bigger than minus 20, that the finite difference approximation gives you a positive definite system, linear system, and therefore SOR is guaranteed to converge by that theorem for omega between 0 and 2. So here's our Fortran program to solve this linear system. As expected, it's quite simple. We're actually trying different values of omega here. We experiment with values of omega between 1 and 1.95, and for each omega we set all the values of u equal to 0, except on the boundary we set those to the boundary values. For linear systems, iterative methods for linear systems, the initial values are not as important. Obviously, the closer they are to the true solution, the sooner you get to convergence, but whether it converges or not doesn't matter, doesn't depend on the initial values, whereas a nonlinear system, it may be very dependent on the initial values. So we've got a matrix U which contains all the knowns and unknowns. Notice it's dimensioned 0n, 0n. When I is 0 or n, and when j is 0 or n, you're on the boundary of that square, and we set the values in the interior equal to 0 for lack of a better initial values. Then on the four parts of the rectangle square, we set u equal to the known boundary values, and we're never going to touch those. We're only going to update the interior ones. So the values of u on the boundary of this square are set to the boundary conditions once and for all. The interior ones are the unknowns that we iterate with. And now we do our SOR iteration. Notice we're doing a maximum of 10,000 iterations, anticipating that it may take a lot more iterations because we've thrown away everything except the diagonal part. However, each iteration is a lot less work because we don't have to solve a big linear system, or we should say the linear system involves a diagonal matrix. So we update each unknown. There's our omega, and this is just our f sub I divided by the partial of fi with respect to ui. Actually, we're using a double subscript notation, so we should say this is f sub ij, and this is the partial of fij with respect to uij. And that's it. That's the whole program. Notice we only update the interior ones, and we don't have to worry about which of these are from the previous iteration because we just use the latest calculated values. So, for example, u of I plus 1 comma j, if we've already updated that, we're using the new value. If we haven't, we're using the old value. So it's actually trivial to program. We don't even have to worry about the n's and n plus 1s in that formula. And notice also we don't have to worry about whether that's a boundary value or interior value. If I is n minus 1, this is actually on the boundary, and it'll be using the known boundary value. So extremely simple. That's the entire program there. Actually a lot simpler than solving the linear system using a direct method. Okay, now let's look at the results of this program. When a is minus 40, remember a had to be minus 20 or more, or it isn't positive definite, and in fact SOR did not converge because it wasn't positive definite. With a equal to 0 or a equal to 40, we did have a positive definite system. Convergence is guaranteed for any omega between 1 and 2. and tried different values of delta x, where delta x and delta y were equal, cutting the value of delta x by 2 each time. And what happens? Well, it looks like there's an optimal value of omega somewhere between 1 and 2 in each case, and the smaller delta x is, that is the bigger number of unknowns, the closer that optimum is to 2. These results are typical. Notice that if we somehow could know what the optimal value of omega to use, then when we cut delta x in half, that is double n, where n is the number of grid lines on each side, then it looks like the number of iterations only doubles. 27, 56, 127, same thing happens down here. If you somehow could figure out how to use the optimal omega, it looks like the number of iterations is just proportional to n. And remember that the amount of work per iteration is obviously order n squared, a double do loop here. So the total amount of work would be n squared times the number of iterations, which is n. So it looks like SOR is going to take order n cubed total work to solve this system if you could use the optimal omega. Well, a band solver turns out to take order n to the 4th. So this is actually an order of magnitude faster than the band solver. This is a two-dimensional problem. For the three-dimensional case, the gains are even more spectacular. Here's summarizing the results. As I was saying, that number of iterations seems to double with n, seems as n doubles, so it seems to be proportional to n. If you were able to choose the optimal omega, even if you just took omega equal to 1, or too lazy to try to figure out the optimal omega, just chose omega equal to 1, that's called Gauss-Seidel iteration, then it quadruples every time you double n, so it looks like the number of iterations proportional to n squared, in which case the total amount of work would be order n to the 4th, which is the same as a band solver for the 2D case. For the 3D case, even with omega equal to 1, it's order of magnitude better than the band solver. In the same section, we try a nonlinear problem using nonlinear over-relaxation method. Apply the usual finite difference approximations to the second derivatives and first derivatives, and you get a nonlinear system. See, the u cubed here makes it nonlinear. Subtract the 1 so that you have 0 on the right-hand side, and that's your f of ij. And we use nonlinear over-relaxation method. Again, it's easy to program. Here's the program. U is stored in a 0 to n, 0 to n matrix. And there's the entire program. Again, we experiment with different values of omega. We set the initial values of u all equal to 0 for lack of a better idea. And here's our Newton iteration, NLOR iteration. There's omega. This is f sub ij. This is partial of f ij with respect to uij. And we're updating uij as uij minus omega times fij over partial of fij with respect to uij. So there's the whole program. It's very simple. Despite the fact that this is a nonlinear problem and the convergence theorems we saw were applied to the linear problem only, and in fact despite the fact that Jacobian in this case is not even symmetric, much less positive definite, the results are pretty much the same for the nonlinear non-symmetric problem. There's an optimal omega between 1 and 2. The bigger n is, that is the smaller delta x is, the closer to 2 the optimal value is. And again, it looks like the number of iterations is simply proportional to n, which makes the total work order n cubed, which is better than the band solver. Now, how do you choose an optimal omega? Well, if you're just lazy, you could set it equal to 1.5 or 1.6 and still do better than the band solver and do better than Gauss-Seidel. But more sophisticated programs will actually solve for omega adaptively. That is, they will take a few iterations with omega equal to 1.5, say, and see how fast it's converging, then experiment with 1.6, and if that does better, stick with 1.6 a while. And by looking at how fast it's converging, they can vary the omega from iteration to iteration until it seems to be optimal. So it is possible to get nearly optimal values of omega, but it's a little bit of work, and it's well worth it for especially three-dimensional problems. Section 4.8 deals with another iterative method that's more popular because one reason it doesn't involve omega to choose. There's no parameter to estimate. It's a little more complicated. The analysis is much more complicated, but it's a widely used method. Perhaps the most variations of conjugate gradient method are probably the most widely used iterative methods. I'm not going to discuss it much in this video, but it is competitive with SOR with optimal omega, and there's no omega to choose. Okay, now let's talk about the eigenvalue problem, eigenvalue partial differential equations. Here's an example, a one-dimensional typical eigenvalue partial differential equation. There's an eigenvalue lambda here, which is not given. We're looking for values of lambda for which this has a non-zero solution. It's a homogeneous linear equation, so u equals identically 0 is always going to be a solution as homogeneous boundary conditions. The question is, for what values of lambda are there non-zero solutions? And if you use the usual finite difference approximation, centered second order finite difference approximations, uxx and ux, what do you end up with? Well, you can probably guess it's going to be an eigenvalue algebraic system. That is, you end up with trying to find the eigenvalues of a matrix, or in a more general case, this is called a generalized eigenvalue problem, AU equals lambda BU, where A and B are matrices. We're looking for a non-zero u, which we're looking for values of lambda for which there are non-zero u's. For the finite difference case, B is usually just the identity, so we're just looking for the eigenvalues of this matrix A, which is going to be tridiagonal in the one-dimensional case. It's going to look a lot like the matrices we've looked at in the last few sections. So we're trying to find eigenvalues of a matrix rather than solve a linear or nonlinear system. As I said, for the finite difference case in this chapter, B is generally just the identity. However, in the next chapter, when we talk about finite elements, B is going to not be the identity, so we're just taking the more general case now. So basically, we're just trying to find eigenvalues of a matrix, and their methods for doing that are discussed in another class, computational methods of linear algebra. We're not going to go into any of these methods except for one in the next section, the power method. Nevertheless, let's look at this problem here. It's a two-dimensional eigenvalue problem, and with the usual finite difference approximations, you end up with a matrix eigenvalue problem, which looks like this. At least the last line looks like that. So we're basically trying to find the eigenvalues of a matrix, which looks a lot like the 2D matrices of previous sections, and we simply, in this problem, we simply called some standard software IcePack routines to find the eigenvalues. Here are the exact eigenvalues of the differential equation. No, here they are. Here are the exact eigenvalues. Here are the eigenvalues of the matrix A when delta x, delta y were 0.2. Here they are when delta x, delta y are equal to 0.1. So this is actually a I believe a 16 by 16 matrix, and this would be an 81 by 81 matrix. any case, the true eigenvalues of this matrix, of the PDE system, there's actually an infinite number of them. The smallest one is 19.74. It's possible to find the eigenvalues exactly of that simple partial differential equation eigenproblem. But there's an infinite number of eigenvalues. They go off to infinity. So obviously for a finite difference approximation, we're not going to even estimate all the eigenvalues. We only get estimates of the lowest ones. And you see that we get good estimates of the lowest eigenvalues, but as you go up, understandably, the higher eigenvalues are not good approximations to the higher eigenvalues of the PDE problem. There's infinite number. You can't expect to approximate them all with the finite 81 eigenvalues of this linear system. So those results were found by simply calling some standard packages for finding eigenvalues, which use some QR method that is beyond the scope of this course. However, we're going to talk about one method for finding eigenvalues that's extremely simple. It only finds one eigenvalue at a time. Basically, it's the inverse power method, and it's basically finds the smallest eigenvalue of this problem. Again, in this chapter, B is usually going to be the identity, so let's assume B is the identity for a moment. So each iteration of the inverse power method, all in the world you do is calculate un plus 1 is A inverse times un, although you don't actually form the inverse and multiply by an. You solve A un plus 1 equals un. So each iteration you start with a initial vector u0 and you multiply it by A inverse over and over. And eventually un becomes an eigenvector, and the ratio of un to un plus 1 is the smallest eigenvalue of A. It's that simple. And there's a variation of this called the shifted inverse power method that allows you to find eigenvalues other than the smallest, however still only one at a time. The user chooses a number alpha, and each iteration now you're starting with a arbitrary starting vector u0, and each iteration you're just multiplying by A minus alpha I inverse. I'm assuming B is identity here. If it's not, then you multiply by B and A minus alpha B inverse. Anyway, you're just multiplying by a fixed matrix every step, actually solving a linear system because we don't want to fool with inverses. Remember that A and B are typically going to be very sparse. Inverse could be a full matrix, and you certainly don't want that. So we actually solve a linear system, but it's algebraically equivalent to multiplying by the inverse, and this will allow you to find the eigenvalue closest to alpha. If alpha is 0, then it's just the usual inverse power iteration. So we can find one eigenvalue at a time, the one closest to given alpha. And by the way, the closer alpha is to the eigenvalue you're looking for, the faster it's going to converge. Notice that you're solving a bunch of linear systems where the right-hand side is changing every step, but the matrix is the same. So this is the ideal case to use the LU decomposition, so that first iteration you solve using, if you use Gaussian elimination, then subsequent iterations, if you save the multipliers, it's going to take a whole lot less work each iteration after the first. So we try this out on a 1D eigenvalue problem, and the usual finite difference approximation gives us a matrix eigenvalue problem where A is tridiagonal, as you might expect, and here are the results. The smallest eigenvalue turns out to be 4.1138. The next smallest is 24.109. We experimented with different values of alpha. Here delta x was 0.01. Try alpha equals 0, and naturally it converges to the eigenvalue closest to 0, which is the smallest one, 4.115. Took 11 iterations. If we set alpha equal to 4, then it converged a lot faster because we're starting with an alpha already close to the true eigenvalue. And then we set alpha equal to 20, and now it converges to the eigenvalue closest to 20, which is 24. So behavior is pretty much as expected.